In this video, we're going to learn how to compute limits at infinity and horizontal asymptotes of rational functions. So here's our first question. We're given the function g of x equals x plus 6x to the fifth, that quantity divided by the quantity 2x to the fifth minus 3. And we want to compute the limit as x approaches infinity of g of x. Also, we want to answer the question, what is the horizontal asymptote of g of x? But before we get into that, let's just focus on the limit. Let's just go ahead and write out the limit in full form, just substituting in that expression for g of x. So we want to find the limit as x approaches infinity of x plus 6x to the fifth over 2x to the fifth minus 3. Now in this limit, as x approaches infinity, both the numerator and the denominator grow without bound. They're both approaching infinity. So it's not really clear what the limit is coming out to at this point. And that means we have to manipulate the limit into an equivalent but different form where we can actually see what's going on here. Now, the way we do this is we divide both the numerator and the denominator of this fraction by the highest degree of x that appears in the denominator. Let's actually write down that rule. Divide by highest degree of x in denominator. That's a super important rule because we're going to be using it for all of the problems in this lesson. Alright, so looking at our limit, what is the highest degree of x in the denominator? Well, in the denominator, there's just two terms here, and only one of them actually has an x, the other one's just a constant, so it's got to be x to the fifth. That is the highest degree of x in the denominator. So we're going to divide both the numerator and this denominator of the fraction by x to the fifth, and ultimately that just amounts to dividing each term in the numerator and the denominator by x to the fifth. So we can just write for each term over x to the fifth. Do that for all of the terms, over x to the fifth, over x to the fifth. And what does the limit simplify to? Well, let's just go ahead and simplify all of those terms individually. X over x to the fifth, that's just 1 over x to the fourth. And then 6x to the fifth over x to the fifth. Well, x to the fifths cancel, and we just have 6 left over. Now in the denominator, same idea with 2x to the fifth over x to the fifth, that's just 2. And then minus 3 over x to the fifth. Now this form of the fraction is actually a lot easier to take the limit of, because a lot of these terms are now going to 0 instead of infinity. For example, look at this 1 over x to the fourth. We know that the limit as x goes to infinity of 1 over x to the fourth is just 0, because the denominator is getting bigger and bigger, while the numerator remains constant. Same idea with limit as x goes to infinity of this term here, 3 over x to the fifth. That's also just equal to 0 in the limit. So really this limit just evaluates to 0 plus 6 over 2 minus 0, which is just 6 over 2, or 3. So there we go. That is the value of the limit. But we're not done yet. We also wanted to answer what is the horizontal asymptote of g of x. Remember, the horizontal asymptote is just the horizontal line that the function approaches as x approaches positive or negative infinity. And we actually just figured this out right here by doing the limit. We saw that the limit as x approaches infinity of g of x was equal to 3. So that means 3 is the y value that this function approaches as x approaches infinity, which means that y equals 3 is the horizontal asymptote. Let's label that HA, meaning horizontal asymptote. Before we go on, let's just talk about one little nuance that will be important later on in limits. And that nuance is that sometimes functions can have two horizontal asymptotes. One as x approaches infinity and another as x approaches negative infinity. So usually we have to check both limits at positive infinity and negative infinity. But for rational functions, both of these limits will always be the same. Rational functions always only have at most one horizontal asymptote. And to find that asymptote, it suffices to check the limit as x approaches positive infinity or the limit as x approaches negative infinity. Either one will do. You don't have to do both. And with that, let's go on. Alright, so here's the next problem. We're given f of x equals x cubed over x to the fourth plus x, and want to compute the limit as x approaches negative infinity of f of x. We also want to answer the question, what is the horizontal asymptote of f of x? But again, let's just focus on the limit for now. So let's go ahead and write down that limit again, using that function definition that we're given for f of x. So this is the limit as x approaches negative infinity of f of x, and f of x is just x cubed over x to the fourth plus x. Now again, as x approaches negative infinity, both the numerator and the denominator have terms that are growing without bound. And do you remember what we did to remedy the situation in the previous example? We just looked for the highest power of x in the denominator, and then we divided both the numerator and the denominator by it. So let's do that again here. What is the highest power of x in the denominator? Well, there are two terms in the denominator. There's x to the fourth, and there's x. Which one has a higher power? This is like x to the power of 4 versus x to the power of 1, and x to the fourth is clearly bigger. So that's what we want to divide by in the numerator and denominator. So let's go ahead and do that. Divide every single term in the numerator and denominator by x to the fourth. So we're not actually changing the fraction at all, just writing it in an equivalent form. Alright, and now let's go ahead and simplify this limit. So this is the limit as x approaches negative infinity of, well, in the numerator, x cubed over x to the fourth, that just simplifies to 1 over x. And then in the denominator, x to the fourth over x to the fourth, that's just 1. And then x over x to the fourth, that's just 1 over x cubed. And hey, look at this. In the limit as x approaches negative infinity, all of these terms here are finite. In the numerator, for 1 over x, we know that the limit as x approaches negative infinity of 1 over x is just equal to 0, because it's 1 divided by the negative of an increasingly large number. And it's the same idea for that other term in the denominator, 1 over x cubed. Same exact idea. It's a constant divided by something that's becoming infinitely large, which in the limit tends towards 0. So this limit is just equal to 0 over 1 plus 0, which is just 0 over 1, or just 0. So there we go, that's the value of the limit. And we know from previous discussion that this limit gives us the horizontal asymptote for f of x. So the horizontal asymptote is just y equals 0. Here is yet another problem for us. We're given this function h of x equals x cubed divided by the quantity 2x squared minus x, and we want to compute the limit as x approaches infinity of h of x. We also want to answer the question, what is the horizontal asymptote of h of x? But again, as we've always done, let's just focus on this limit first. So we want to compute the limit as x approaches infinity of this fraction x cubed divided by 2x squared minus x. Now, in this fraction, in both the numerator and the denominator, we have terms that are tending towards infinity as x approaches infinity. So it's not clear what the limit is off the bat, and we have to apply the same procedure as we've done for all the previous problems. We look for the highest power of x in the denominator. Here that's just this x squared here. And we divide both the numerator and the denominator by this highest power of x. So go ahead and divide the numerator by x squared, and all the terms in the denominator by x squared as well. Now we simplify all of these terms. So this becomes limit as x approaches infinity of, in the numerator, we just have that x cubed over x squared, that's just x. And then in the denominator, 2x squared over x squared, that's just 2. Then minus x over x squared, that's just 1 over x. And now looking at these leftover terms, we see, first of all, for this 1 over x term, we know that the limit as x approaches infinity of 1 over x is, well, just 0. Now, in this case, the numerator here has a term of x, which doesn't go to 0 as x approaches infinity. So why don't we just go ahead and leave that in the limit for right now and just simplify with this denominator term. So it's limit as x approaches infinity of x over 2 minus 0. And that's just the limit as x approaches infinity of x over 2. Now as x approaches infinity, this numerator grows without bound, while the denominator is constant. So that means this fraction, x over 2, is approaching infinity. So that is the limit. Okay, now what about the question, what is the horizontal asymptote of h of x? This is a bit trickier now because we don't have a single number that the function is approaching as x goes to infinity. The function is growing without bound, so it's really not leveling off at any horizontal asymptote. So that means there is no horizontal asymptote. It was a trick question. So no horizontal asymptote. So the takeaway here is that whenever you want to compute an infinite limit of a rational function, all you have to do is divide by the highest power of x in the denominator. And then it'll simplify into a form where you can actually take the limit and get a straightforward answer. Now, if the result of the limit is finite, then it tells us the equation of the horizontal asymptote, just y equals whatever value you got for the limit. But if the limit is infinite, then there is no horizontal asymptote. And that wraps it up for learning how we compute limits at infinity and horizontal asymptotes of rational functions. In the future, we'll continue learning about ways to evaluate even more complicated limits, such as using the method of the squeeze theorem.